on Kaggle, you learn how to validate your output. Because if you don't have like essentially the perfect cross-validation pipeline setup that takes into account all the cheating that your model can do, all the like weird instances where this could be correlated with this, if you don't have a good cross-validation going, that means you're not going to win.
Hello, everyone. Welcome to the Data Scientist Show. Today, we have Jesper Dramsch. Jesper is a scientist for machine learning at the European Center for Medium-Range Weather Forecasts. They have a PhD in applied machine learning to geoscience from Technical University of Denmark. They are a Kaggle kernel expert and TPU star, ranking at the top 81 out of 100,000 worldwide. Jesper talks about machine learning and career in their newsletter, YouTube channel, and at scientific conferences. And today we'll talk about machine learning in weather forecasting, their career journey, and reproducible science. And if you like the show, subscribe to the channel, give me a 5-star review, and leave a comment. Welcome to the show, Jesper.
Thank you so much for that kind introduction.
So how did you get into machine learning?
The complete origin story is that I started my PhD and like my complete background is geophysics. So not actually machine learning or that stuff, but during my PhD, we were really new with the institute and we had some problems with getting the data. So I started taking courses and one was on advanced image analysis. And one of the lessons was about neural networks. And they did the smartest thing ever. They made a small competition and I completely focused on it. Like I didn't do anything else for that week and programmed a small neural network to classify MNIST data from scratch in MATLAB without any imports. And that is when I realized how useful this is like in real world scientific applications. And yeah, I completely switched my PhD over in that direction at that point, basically.
Yeah, I have similar learning experience. When I first took a machine learning course, we have to derive the loss function by hand. It seems very tedious and painful in the beginning, but it gives you more confidence later when you download the package because you know exactly what you're doing.
Yeah, 100%. Like I exactly remember when I had to choose between two and I would like implement both and just try it out. It's such a good learning mechanism. It's like this first principles approach that a lot of physicists take as well. And yeah, I agree. It helps so much.
Can you tell us what do you do now? What's your day-to-day like?
Yeah, so I'm a scientist for machine learning at the ECMWF. And that means my job description is basically to talk to a lot of meteorologists, climatologists, and computational scientists and basically figure out what they're doing and how we can help them with machine learning. So find places where our physical understanding either is too expensive or isn't high enough because there's too much noise. And either help or implement for them machine learning systems that essentially do that job that classical physical approaches can't really do.
Can you give us example? For example, I know you work a lot on weather forecasting. What type of data do you use? What type of model you solve that problem? And what would be, for example, the outcome, the output variable look like?
That is a really good question. So I work on a couple of different applications. One, for example, is called observational operators, where we get weather data from so many different data sources. Like planes always give us information. Then we have weather stations all across. Sometimes in theory, you can get data from citizen weather stations. So you have all these different kinds of inputs. I mean, planes don't fly all the time. They don't fly at the same location all the time. So the location is variable and the recording time is variable. And then also you only have spotty information about the weather. But when we do weather forecast, we want a field, right? If you see the weather forecast, you see like the rain front and everything. Like the weather forecast from TV are exactly what we want out of our system. So somehow we have to translate this data that is, super spotty in every dimension, essentially, and have to translate that into something that we can get fields out of. And this translator is essentially the observational operator. And that is something that I'm working on. So we have some satellite data, for example, which we can also use for this. And we derive some of the fields that we can then put into our physical system and improve weather forecasts that way. That's one of them. Another one is fairly simple. You take the weather forecast that is already done. So one trick that we use in weather forecasting a lot is we slightly vary our starting conditions, so we get different outputs. It's called as ensemble, just the way it is called in machine learning. And by having this spread over an ensemble, we actually get a lot of information about like the variability and like how certain our weather forecast is, just like machine learning. And we can use machine learning to reduce the bias in this forecast, and basically take the raw forecast, put it through a machine learning system that is used to this kind of data, trained on this kind of data, and bias correct it. We actually just had a big like Kaggle challenge about that with some really cool applications.
Oh, cool. Thanks for sharing that. So the ensemble you mentioned is more like a simulation of multiple scenario, and then you do ensemble.
Yeah, exactly. Yeah, sorry, I'm skipping a couple of steps. So
no worries.
Totally
I kind of skipped through the PhD dissertation video. So I learned a few terms and then I note down some questions. So I know you're using kind of a simulation together with machine learning. And so for the machine learning part, what type of model or approach do you use?
Actually, like if you name any, we try it. So on the observational operators, I am working with XGBoost at the moment because it's very, very cheap, very fast. I can iterate on that really good. And of course, I get like the feature importances quite quick. Because I'm working with domain scientists, I have to put a lot of focus on explainability and on making sense of the model. So XGBoost is really great at that because we do get the feature importances. But on another problem where we don't have to communicate that much, we're going all the way in using a combination of convolutional neural networks and transformers. So really all the way.
Yeah, got it. So it depends on the type of the data. If you have tabular data, you use XGBoost or tree-based model. And then if it's related to image, you use deep learning or transformers.
Exactly.
Yeah.
And I follow like all the common advice. Just like you said, that distinction is perfect. And the same if we have like this field data that I'm talking about, like CNN is great for that. So a convolutional neural network is great for that because they're good at correlating the spatial dimension. And
Okay, great. So I would definitely want to talk about how you use images and the convolutional neural network. And let's start with XGBoost. So you mentioned sometimes the data is very sporadic. And is it one of the reasons you choose XGBoost because it can handle like missing data really well? Or do you do any like pre-processing when you have those type of data challenges?
Both. So basically, in my experience, which is obviously limited, but in physics, you always have noisy data.
Yeah.
There's never clean data. So you always have to do some pre-processing. If we work with subsurface data, there's usually we call it signal to noise ratio, which is that the signal is just hidden inside of all the noise. Like all the different, like in seismic, we have the problem that we have noise from everything. For example, from just the power. So power is at 50 hertz. So when we record our data, we can actually see a really loud spike at 50 hertz. And we always have to calculate that out. And in satellite data, because the satellite isn't always at the same location, we always have to somehow do data assimilation before we can even look at the data, because it's saved in a compressed state. So always both. I love XGBoost for dealing with nans really well. Like, it's just the best way. Like, yeah.
Yeah, thanks for sharing that. And weather data also have their seasonality patterns, right? If you look at that. So how do you use XGBoost to deal with the seasonality factor? Do you train another model just to take care of the seasonality?
Right now, I don't, because I have enough data to just simply learn the seasonality patterns. I think it's always a trade-off between data and application. So in my case, I specifically want to be able to model the seasonality. So if I can't do it implicitly with a model, I would definitely do some kind of kernel method probably that can model the periodicity in our seasons.
Oh, so you have you model the seasonality separately. You kind of just add it on top of the prediction. You
could, but I don't. Also, the problem is I'm working with global models, so seasons are different everywhere. So somewhere you simply don't have seasons. So it's really, at that point, I'm simply relying on XGBoost taking care of it. And one of the most important parts there is to have like a good validation pipeline, right? You have to make sure that your validation set is decorrelated from the training set. And that's something that I spent most of my time thinking about. How could my model trick me, essentially?
Yeah. And when I think about weather, it's always by location. Can you explain a little more about what exactly are you trying to forecast on the global level?
So one of the there are two super common variables that I deal with at the moment. One is rain. So essentially, we call it total precipitation, but that is literally just measuring how much precipitation, so rain, snow, hail we have. And the other one is temperature. So it's the 2-meter temperature, which is the temperature at 2 meters above ground, essentially, that we try to model. And those are super common, but we do have others as well. So we do have groups that work on flood modeling. We do have groups that work on all different weather phenomena. We have a really interesting machine learning application with tropical cyclones, which are also really hard because you want to predict the trajectory. But like, how do you do that if you don't have that much training data? Tropical cyclones aren't that common. So it's a question, how do you deal with this sparse data and still get a good machine learning model out of it? Yeah. My colleagues have done some really good work on it, actually. Like, it's impressive, I think.
Yeah. So besides picking models like XGBoost, what are some other best practices or method you find useful when deal with sporadic data?
So I try to stay away from interpolation too much. So I just wrote, so it's kind of funny. I think last week or the week before, I just wrote like a very long piece about missing data in my newsletter. And basically there's some really, really interesting research from Gael. He's one of, I'm saying his last name funny because I can't say the R right, but he's one of the core contributors to scikit-learn and the director of research at INRIA here in France. And they've done some fascinating research on imputation. So do you interpolate your data if you have missing values? How do you deal with this? And yeah, some of the learnings from that is XGBoost or of course, they use the scikit-learn variant, like the histogram gradient boosted trees, but it's XGBoost under the hood. And essentially, that one is really good. Or doing mean imputation and having a flag, essentially. So adding another column where you say this was a missing value and this wasn't. And that way you can have give it to a random forest, for example, that doesn't deal with nans in this case, and it can still learn with full data, but it has an indicator when there was missing data, so it can actually learn better. And that is one of the best ways to deal with it. But yeah, XGBoost is just really good. And most of the sophisticated imputation methods, so methods that do it iteratively, they're really expensive and often they're worse. So
yeah, thanks for sharing that, because in theory, we'll learn a lot of method like imputation, right? You can do a lot of fancy things, but you actually, unless you really know what is it doing, or you really believe the way it imputes match the distribution of your data, otherwise you're introducing new type of noises that you don't fully understand that might actually make the result worse. And I might ask you to share the link of the paper or of adding a new column. I want to take a look at that. I haven't heard of that yet, but that sounds like a good approach. Like you basically tell the model, hey, those are the rows I imputed. That might not be the same of the original data. So maybe the model will learn something from it. That's very interesting.
I call it missingness as a feature. I don't know if that's a thing, but it's really like I've seen it on Kaggle as well, I think, and it works so well.
Mm-hmm.
Yeah.
Yeah. And you mentioned, the name of the center is mid-range. What's the definition of mid-range compared to, I'm sure there will be like short range or like a long range.
There's all kinds of ranges. So it goes from seconds out to hours out. That is called nowcasting. And I should really know this because I work there, but I'm not a meteorologist and I'm terrible at these kinds of details. But as far as I understand, the medium range is like a week out to a couple of weeks. So this S2S data that I was talking about all the way in the beginning, it's called subseasonal to seasonal. That is so a subseasonal prediction would be in the area of a couple of weeks, so 1 to 4 weeks, and one to 2-3 weeks, and then beyond that you have seasonal predictions. And I'm honestly still learning these terms as well, because every time you go to a new field, you realize that they have different words for everything.
Yeah.
So you might be talking about the same thing, like you might be talking about models, but the meteorologist thinks about a completely different thing than you as a machine learning scientist, and it makes it very interesting, but it also makes it kind of hard sometimes because there can be misunderstandings there.
So I think I was reading a book called Super Forecasting. It mentioned when we predict, so first weather is really hard to predict, and then sometimes if you have those type of short-term prediction, it's easy for you to get immediate feedback to compare your forecasting to the results. So it's easier to tune the model. So I'm curious, what are some challenges in like mid-range? Are you able to compare the actual weather, the ground truth versus your forecasting? Do you have to wait a long time? How does the kind of model retraining works?
It brings us in a really interesting problem, because like you said, if you have immediate feedback, you also don't have to have that much data.
Right.
But at ECMWF, we have the largest weather storage in the world. And in my experience, the longer the timescales also means that you virtually have less training data. So if you actually want to move further out, that means your moving window is much less data to train your model on, because you have much less like diversity in your data set, and much less, like a much smaller probability of actually modeling the entire let's call it decision space, or like the entire system. And I think we're going back until 1950s or something like that with our data, and that obviously is really problematic, because we're we're basically starting right in when anthropogenic climate change is already in full gear. So everything is changing under your feet, essentially. And how do you guarantee that you validate your models enough? And it's, you have to have all that data. And I think, so ECMWF has done some work where they basically go back to the measured weather predictions and basically pretend that they predicted on those conditions. So this type
testing.
Genau. This is what we call hindcasting in this case.
Okay.
And we have a very large data set that is also used in a lot of papers for this specific reason, because otherwise you have the problem that with purely measured data, measurements change. Like a lot of centers then decide to go to weekly predictions instead of bi-weekly predictions. Some centers change their algorithms because we always want to get better, right? So that means that the prediction becomes better over time, but that also means our system completely changes. In addition to the physical systems, also our prediction system now changes. So this kind of hindcast is a way to introduce a bit of stability in the data sets that we have. And I think a lot of people are really appreciative of this kind of work, because that means you can take one of the variables out of the equation, essentially, and keep it constant.
So is that based on a assumption that the weather or at least the variable you're predicting doesn't change that much across those decades?
In this case, because we're using physics to do the hindcast, it doesn't matter that much.
Yeah.
Well, of course, it matters to the degree that it matters, but I don't want to toot my or our horn too much, but like the people I work with are really impressive, and it's kind of like intimidating a lot of times, like how good everyone is at what they're doing. But it's like everyone is like working on their very small thing. So it's like this huge model that has all these different things that improve over time. So that way we can predict and have like the best prediction based on the model that we can have. And of course, there's a lot of papers that we try to incorporate or that are published by us. And that way we hope to have, and like in a lot of cases, we do have a very good prediction in that case.
Yeah, thanks for sharing that. And previously, you also mentioned that you spent a lot of time thinking about how to validate your model. So besides the what do you call it?
Hindcast.
Hindcasting. Yeah. What are some other ways you validate your model?
So one classic one is so the thing that they teach you in school that you never do is actually super, super important in actual work, where you build a baseline model based on an algorithm that already exists and is validated. So on some of the work right now, we're taking some of the classic statistical methods that are used, and we're comparing our work against it. So if you have a strong baseline and you compare your machine learning model against it, you can actually say if you're doing better or not. And this is also something really interesting. This is going to be a tangent. I'm really sorry. Stop me if it's boring.
No, I love this topic. Please go on. Yeah.
Awesome. Like the first thing that I had to learn is that basically in forecasting, we have an entirely new set of metrics. So of course you have like mean squared error, because we're still in physics and we just assume that our errors are Gaussian and stuff. But if you have probabilistic forecasts, so this kind of ensemble forecasting, we go in a direction where we have to measure it a little bit different. And those are called skill scores. And actually, if you go over to language models, they often use I don't know how to say it correctly. Is it Brier score? It's one of the metrics that is also in the new Hugging Face Evaluate library. And it's quite common over there. And it can actually be used for evaluation of forecasts as well. We usually use something different. It's called CRPS. CPRS. I always mix them up.
Oh, what's the definition of it?
It's basically a ranking of your probabilities. And that way you can guarantee. So in GANs, they use this Earth mover distance, right? The Wasserstein distance, which essentially is the energy of moving one probability to the other. Now, the problem is that you can move any point from this probability to any point in the other. And it's kind of, it's not defined where exactly it has to go. It just has to kind of go over there. And these skill scores are a more formal way of this, in always having the same kind of value for modeling a probability that is moving from one to the other. This is also, I think you'll notice I'm very bad at like strict mathematical definitions.
No, it's okay. It's just like a high level. Yeah, just want to give the audience like an understanding of the metric you're using. No, it's all good.
Yeah, essentially we want to see that the spread of our output of our different ensembles from the simulation is as close to the actual weather that we recorded as possible. And these kind of metrics are really important in forecasting. And I'm still reading about them because it's like it gets very mathematical very fast. Realizing that these specific metrics that someone uses in a specific domain, that's also really valuable in a way.
Yeah. So I think it's very interesting because I do see a lot of similarity, like the score metrics you mentioned from language models, because you're both dealing with sequence, right? So that's why you can borrow some, maybe you can also use some type of transformers, encoders similar to language model to deal with the sequence. Have you tried that?
I think it's just outside of frame here, but we're actually working on a paper using transformers for this kind of work. It's super fascinating. So there is a paper out by a guy called Finn who used transformers to correct ensembles, which is fascinating. And I think everyone in our group has been reading that paper. Like, it's from last year, and it was fascinating, like some really, really cool work. So yeah, like transformers are eating the world, and same in physics. You can apply them to this kind of problem really well, because the context between different outputs in your ensemble forecast is really important. So we call them members. So each sample in this, each individual forecast in this ensemble forecast is somehow related to the others. And there's information in there that you can often harness, and transformers are fantastic at this.
Yeah. So besides that, what are some other benefits of using transformers?
So a really simple one. Usually what we have to do, because in our actual like production systems, we have 50 forecasts for every forecast. Well, 51, but rounding errors. Yeah. And usually you can't take all that information and then correct it. So what most people and most systems do, and it works well enough, is just take the statistics of it, so take the mean and take the standard deviation and correct it as if it was Gaussian. But of course, that is an assumption that you're making about your forecast, that it is distributed in a Gaussian way. So usually you would do that and then taking an ensemble transformers from that paper. So I'm just reciting that paper at this point. I hope that's okay. But the idea is that you can now move each individual transformer. And the next cool thing is, because transformers work on arbitrary sequences, is you can train it on a fairly small number of forecasts, and then you can put it on any kind of ensemble forecast. So that means we can train it on like a super small one with maybe 5, maybe 10, and then we can apply it in production on 51, which makes our experimentation much faster if we wanted to do that, right? Because we can apply this to much smaller data sets and train, and at inference, the model is much cheaper to run, because you don't have to calculate all the soft max anymore that you have in a transformer. And the inference is faster, is cheaper, so you can run it on more data, essentially. So this is also really cool.
Yeah, thanks for sharing that. I have a similar experience, not using transformers, but other deep learning models when I do a video processing model, like a video recognition model. So with those very advanced deep learning architectures, I was surprised how little data I needed to train it. I thought I need a lot of video clips, but I think for that specific project, I only had something like 200, 400, so less than like 1,000 examples. But I think if your the model kind of it's maybe similar to how the deep learning architecture the model was kind of trained on, you actually don't need a lot of data. So, but it's like case by case. But sometimes I'm surprised how deep learning model work well on some small data set.
For sure. Also, something that I found very early in my PhD is that even if you're working with physical data, you can't underestimate transfer learning from like an ImageNet or something like that.
Yeah.
Because they have such a diversity in training data, they're generally enough that you can fine tune the model on some physical data in a lot of cases, and that. Like for me, that was a game changer, because in the beginning of my PhD, there was basically no open data. So I had to train it on essentially patches from 2 large pictures. And so the validation, again, was really important, because like this is so prone to overfitting, but it worked better to, back in the day, do it on a VGG16 network. Than a convolutional neural network that you train from scratch just on the data. And I think this also is very congruent with something fascinating that they learned about training supervised, that you want to pre-train your neural network on just diverse data, and unsupervised, you can do that. And then you want to fine tune it on the actual training data that you want. And that way you get really high scores on ImageNet, for example. I think I heard Jan LeCun talk about it, maybe Ian Goodfellow, someone of them. But yeah, it's pretty much accepted at the moment. Of course, further research like this will come out at a point in time, and like 5 years down the line, someone will hear this and will maybe hear this and say, that's wrong. Well, that's because research probably moved on from that and actually found a way to do proper pre-training, but proper supervised training. But yeah.
Yeah, that's very exciting. Thanks for sharing that. And you mentioned sometimes you need to interpret your model. So when you use transformers, are you able to understand what the models are learning? What are the important features?
In a way, yes, but you have to be careful. But so, for example, we have a look at the attention in the transformers, because the way that the transformer is making connections between your your data is super valuable.
Yeah.
And I know that some people say this isn't proper interpretability, but in a way, I think it's at least a step in the direction of understanding your model better and how your model interprets the data. So that is already valuable and an insight into what's happening. And I think one thing I learned very quickly, and I think a lot of data scientists learn, is that the expertise of domain scientists is never to be underestimated.
Yeah.
These people have degrees and years, decades of experience. And this doesn't come from nothing. Like maybe 1 out of 50 assumptions is a little bit wonky. And you're like, we can probably do better. But most of the assumptions are correct. So if you show, for example, the attention layers and how the attention makes connections between your data to an expert, they can tell you if this makes sense or if there is some spurious correlation going on that your transformer is picking up. So essentially that it is like a mild form of overfitting and just picking up on something that physically doesn't make sense or whichever domain you're working in. So yeah, like in that sense, I think looking at the attention layers is fantastic.
Yeah. I think that's very important. Like machine learning is not magic. It's important to understand that and compare that to what domain expert recommends, because they might learn a lot of things from qualitative methods, right? Or some type of theories that doesn't require machine learning. And so you can basically learn from those type of knowledge and feed that knowledge in your model. It's not directly a feature, right? But it's through human to transfer that type of learning into the model. I think it's always interesting. And another thing I think is very interesting is you also work on a lot of physics simulation. So it's kind of, you're at the intersection of, I have a formula, I don't need data, right? I have this understanding of truth. And then I also build this model, assume I don't know the formula, and then to see if I can learn something from it. And you combine this, physics, truth, to things learned from machine learning, and then you combine these two different type of knowledge together. So you can kind of offset the, blind spot from each side, because I think that on the physics side, the truth, the theories are right. I mean, in theory, but in reality, there's always something happens. There are a lot of noises, but the model sometimes might, overfit. So you might want to kind of correct a little bit, looking at the, those type of formulas.
Yeah, definitely. This is also something that I noticed in, like, even before I went into machine learning. I work with wave equations a lot, and in the beginning you just say, okay, we look at the wave equation, so a wave that goes down and up once is just reflected once, and then you realize, but a wave that goes down, up, once, we can actually get information out of that. And then you realize that something that hits something really small and then is scattered in all directions is really valuable. But all of those iterations that I just said have been evaluated as noise, as something you just throw away and want to filter out of your data before. So we always make assumptions, even in our physical understanding. And it's always like we have this wave equation and then plus S, because we somehow have to put the noise into our equation. But what we consider as noise is also really important. And I think like, ironically, so I know that like old neural network understanding is that neural networks can't deal with noise. And my opinion these days is that neural networks are fantastic in the noise. We have a really good understanding of the main signal, but then like modeling the noise, modeling whatever it is that we can't really model because it's too expensive or too small in our physical systems and also in a lot of other systems. Like this nuance is really good, where we can put like a machine learning algorithm on top and learn that difference right there.
Mm-hmm. Yeah. Thanks for sharing that. And now I'm going back to the topics on your models on images using convolutional neural work. Can you tell us about what type of image are you learning from and what are you trying to classify or predict?
I'm not exactly sure what you're asking.
Oh, I think you mentioned convolutional neural network. Do you mean to use convolutional neural network on your tabular data, or in your work, do you do any image data processing?
Oh yeah, convolutional neural networks are great on images because in an image, if you look at the image of me, like everything that is close to each other matters more than like whatever is here or whatever is here. Like if you want to classify, is there a person in here? You want to look at the center of the frame. And we can and use a lot of this in a bunch of like physical data, in satellite data, in any measurement that has some kind of field. So if we're looking at field data from like whatever you see on the TV and the weather forecast with your weather fronts, then convolutional neural networks are fantastic at this. I've heard this called the inductive bias of convolutional neural networks before because of this bias that they know things that are close to each other are more important than things that are further from each other. But then you still build on top of each other and you get all this context because you have this neural network that is layer upon layer upon layer that is getting a lot of context out of it. You can perfectly use this in X-ray data. So I applied it to medical data on Kaggle before, in seismic data because you have this seismic field that you can work on, which is essentially my entire PhD. And you can also do it on satellite data, which was my first job, and now on weather data, which is my current job. So it's so versatile because it's a black box. It doesn't make any assumptions except for that everything that's closer to each other is more important.
So when you apply that to weather data, what type of weather data do you use convolutional neural network?
So a common one, like I haven't worked in this job long enough, so I'm gonna get back to a lot of the things that I said before. But the model that is correcting the prediction of our seasonal forecast, we tried some convolutional networks on that. So we had a look at the fields essentially. So that was temperature and precipitation again. Sorry, but use those. And in the competition that we had, one of the models was fascinating because they used a bunch of different inputs. And so one of them was looking at the orography, so essentially like a height profile of the world, and taking that as an input as well, because that is also really great in a convolutional neural network. And a bunch of other data like wind data, you have wind fields. So you know at what time did the wind blow in which direction, it's essentially.
Oh, interesting. So it's a kind of high dimensional data for wind, like the time, location. Got it. So for example, wind, this feature itself, it's like a kind of high dimensional matrix, and then you can put it into did I understand it correctly?
I think, yeah, it's close enough. Like the thing with those higher dimensions is, of course, you can split them up if you want. So because in wind, we always have direction and velocity. We just treat them as two fields, for example. And that way we get rid of one of the dimensions and just use two inputs. That's one way to simplify it. But yeah, exactly. So even if we have this super high dimensional data, we can often use a neural network, like a convolutional neural network on it, because we just use a 3D convolution and basically pass it in this stack of high dimensional fields.
Oh, okay. So when you say field data, what do you mean by field, the weather field data?
So field in this case is if you look down on a map like of the US or wherever you are, and you have a measurement of your rain, or if you look at the temperature, any of that is a field, because you essentially have like a 2D map of whatever variable you're collecting, and that is kind of field data. So it's basically just an image, like a 2D, usually 2D recording of whatever you're measuring. So if it's your wind, like in the US, I know you have a lot of wind, especially over the more flat plains. You have very fast winds in a certain direction, and then when you get to your mountains, you have wind on the one side, but it kind of stops on the other side, and you can just record that as a 2D map of your wind. So when I'm saying fields, it's often maps of a thing.
Oh, got it. Yeah. Okay, so yeah, that makes sense. So it's kind of like a map, and then they put it into the convolutional neural network, and then because convolutional neural network so our humans, like pictures, it learns from our features. Do you also look at what type of the field, what the shape of the field does the convolution model learn?
I've done less of that. Especially like the work that I'm doing right now with weather data is fairly young, so I don't really have anything to look at yet.
Yeah.
But especially with so I remember these really cool images, and I still use them for teaching because they help people understand where you see in the beginning you have these edge filters, and then they get into like little shapes, and then you can actually see faces. But that is only partially true for modern neural networks, I think.
Yeah.
Because in a lot of cases, like if you have like a ResNet, because of these residual connections in these super deep neural networks, we don't have a lot of that interpretability anymore, because you don't even know which layer to look at, because there are like hundreds of layers sometimes. So it makes it hard in that way. But on the other side, I think SHAP, our favorite interpretability library that everyone uses apparently, it has the GradCam algorithm in there, where you can see where the neural network puts its attention on. So that one is fantastic, I think, and also quite valuable. But you don't really get this layer-wise interpretability anymore, of course.
Yeah. Thanks for sharing that. So we talked about sometimes when we deal with weather data, the data is sporadic. So what are some other challenges in your current work?
Validation for sure. So, and it's one of my favorite topics, because you imagine that you have a bunch of weather stations and you randomly separate them. And there are some that are closer to each other, right? And if you accidentally split, like in San Francisco, you probably have 2 weather stations. So if you split one into your test set and one into your training set, you're kind of cheating, because I know San Francisco loves to talk about microclimates, if I've learned anything about people living there. But like the overall weather is usually kind of similar, even if you have a little bit of separation through your microclimates in there. But like that makes it really difficult. So every time you have this spatial dimension in your data, you have to be super careful how you separate your data. And if you're building global models, like I mostly do, you have to be like, how do you build a model that accurately models everything if you have to keep some of it out of your training data? So oftentimes we then use all of it as training data and take a different year, so with a gap in between, for validation, which makes it less accurate in the spatial dimension. You definitely can have some overfitting there. So you have to be quite careful what you're doing there, and do a lot of like inspection of your models and your inputs and outputs. But then you can at least do it on a different year, where you have a bit of a different climate and a bit of a different weather, even in the different locations. So looking at those correlations of your validation is really tricky.
Yeah. So when you do kind of model evaluation, validation, what type of metrics do you generally use?
Depends a little bit on the problem, but in a lot of cases, mean squared error or the skill scores that I talked about. So yeah, in forecasts, you want to evaluate skill score. In a lot of the classic modeling, but one thing that I notice, especially in weather, so if you, for example, look at rain maps over the UK, you can always see that everything is fairly smooth, but then you have some extreme rain events. Like there's always some torrential rain somewhere. And if you look at the mean squared error, for example, that one really has this problem that if you predicted 1 pixel to the side, you get a really, really high error, but it's almost in the right location. So one metric that I really like for that is called the Hoover Loss, which is, it is still convex in the middle, but then it just goes linear out. So it's a mix between mean squared error and mean absolute error. Someone from like professor in information theory from Stanford recommended that to me. And I've been using it a lot in these kind of things. And one time it actually saved the model that we were working on, not at ECMWF, but at my job before. It performed better than anything else. Like it was able to get up to the performance of GANs, but as a cheap model that was just a UNet. And if you have these kinds of problems where you have extreme values mixed in with like fairly smooth data, like the Hoover loss is fantastic for that.
Yeah, I haven't heard of it, but it does make sense. Basically, it reduces the weight to the the squared value. So if you have it's kind of avoided the extreme values weights. Have you tried, I think, similar kind of idea? Have you tried to do like a log transform of the mean square error and add some weight to the original mean square to kind of reduce the influence of outliers?
I don't think I've done that, but with the precipitation data, you do have to always transform it somehow. And if you ask different meteorologists, they will use different transforms for it. But it is essentially, you have a bunch of places that have no rain at a time, and then you have a bunch of places that have a little bit, and then a bunch of places that have a lot of rain. So you always have to transform your variables. And obviously your output. So in that sense, definitely. So like whatever is appropriate for the data. And there it's also interesting because the domain scientists have been doing that for decades usually, so they can tell you. And if you have a look at how do people transform rain, essentially they either use like the cubic root, I think the fourth root, or exponential. And some people have arguments for those. And in machine learning, you just try which one works best on your problem.
Do you have any preference of what transformation generally works better, or you just try all of them and see which one works better?
I'm fairly lazy, so usually I ask people because they've been working on this the longest. But I find the easiest way is to look at the distribution of some data points. So just take a sample into pandas or whatever and just get a KDE out of it and see how it's distributed. And then usually you can compare it to like the most common distribution. So if you have a Poisson distribution, if you have a Gaussian distribution, you're fine. And then you can usually see how you want to transform your data. And also oftentimes what kind of metric you want. Because if you suddenly find that your data is like binomially distributed, you probably want to use something else than mean squared error. But that's obviously like depending on the model that you use and all that stuff. So looking at the data first, but then in a lot of the cases, where I just have this almost exponential. I just log transform it because it's cheap and it works in most cases.
Right. Thanks for sharing that. So I know you did a lot of Kaggle, work a lot on Kaggle competition. You're a kernel master. Are you still working on any Kaggle competition or project right now?
Not right now. I have been looking at it because I'm not yet a master. I have to get, so I'm actually one medal away from a like notebook master as well. So I'm like, should I do it? But I usually, so the problem with me is I probably have ADHD. So I have to find something that I get like super focused on. Like all of the notebooks that you find from me were just me sitting awake like an entire night and just programming something and putting it out there. And yeah, usually people really like it. But so far I haven't found a problem that I found like super interesting and where there weren't like awesome, like the Kaggle has changed. There are now professional people that basically write notebooks all the time. Like NVIDIA has some professional Kagglers. H2O has professional Kagglers. So me doing this on the side, I feel like, maybe I'm just deemed to stay an expert, which is completely fine. Also, I'm never gonna get beyond rank top 81. Like I dropped to like 400 or something now, which is still fantastic. Like I'm not complaining, but there's no way that I'm ever gonna get above that without making that my full-time job. And it's not paid that well.
Yeah, I think it's more of a way for us to, learn or share our knowledge. So what are something you learned from working on those Kaggle data? And have you transferred any of those learnings to your current work?
Oh, for sure. Every notebook, every competition that I worked on, I learned so much. Like me harping on about validation is entirely from Kaggle. And it's kind of funny. People really like to hate on Kaggle because they're like, it's not data science. And like, yeah, it's not. It's a machine learning competition website. Like it's a super small part in the data science workflow, right? So it's just the small modeling part. And I totally get it. It's not data science. It's mostly a little bit of EDA and mostly modeling. You have a very, very nice data set already prepared for you. And if you get to a company, you rarely have something like that. It's usually like a lot of the data science work is preparing the data, getting the data from stakeholders, having communication about what the actual KPIs are that you're meeting. So all that is not done on Kaggle, but from all the modeling, I feel like in most machine learning courses, and I really don't want to like bash on university courses or all the courses that are out there. Like they do amazing jobs. I took so many of them. I love them because you also still learn something. But on Kaggle, you learn how to validate your output, because if you don't have like essentially the perfect cross-validation pipeline setup that takes into account all the cheating that your model can do, all the like weird instances where this could be correlated with this. If you don't have a good cross-validation going, that means you're not going to win. Like absolutely not. And that is also one of the reasons why I never won a competition. It's so much work figuring all that out, and like so much respect for the people that do. Because like even at my current job, it's hard to figure out how you validate your data properly. But it's like, all right, but if you're like literally chasing the fourth digit after the comma, yeah, you better, well, it takes a little bit of luck, but also a lot of knowledge putting into there. And of course, all the programming that I did for it, like writing data loaders, I kind of got started on Kaggle and then took a lot of that knowledge into other domains, because I started writing on Kaggle in 2018, I think.
Oh, wow.
So like it precedes the first paper that I published in my PhD. So a lot of my decisions that I made in my PhD were based on knowledge that I got there. And like, I think it's really valuable in that way. Also, like how you build different architectures, and then all the tricks that people use in architectures. And then, like, beyond what I did, people share so much, and I love looking. So when I have a new problem, especially in my old job where I had so many different difficult problems, the first thing I did was have a look at Kaggle if someone did something similar.
Yeah.
If there was a competition or a notebook or something like that, and see what people are doing, because people are really, really creative. So that's kind of what I took from it, like not underestimating how valuable the platform is. And also, like all the little tricks. I always had this feeling that there are these little tricks that you have in neural networks. And then the ConvNext 2020 paper came out, which was essentially, so convolutional neural networks are kind of bad, right? They totally lose against transformers, even in images at this point. And then someone took like all the little tricks that you can use in convolutional neural networks to make them better and match performance of transformers. And that was fascinating. And I think that's also what's mirrored in my experience. You can find so many little tweaks and tricks, and simply like going away from the default settings in a lot of the neural networks is already so valuable. And then, of course, so you mentioned in the beginning that I'm a TPU star, which is a funny title I got on Kaggle, but I take it. And that was me learning to deal with different architectures. It's fairly easy to just, if you have a single GPU in your PC, like the big one standing next to me, like that's easy to train on. But how do you then scope your solution and put it on a TPU? How do you scope your solution and have like a strategy to put it on multiple GPUs? And all that distributed learning, that is definitely something that where the thought process for me started on Kaggle. And all those small things kind of.
Yeah, thanks for sharing that. Because I sometimes kind of have those conflicting ideas that I think sometimes data scientists spend a lot of time doing some small tweaks and here and there, but sometimes you get more gain, like ROI, to go back, have better data, or try maybe a better model. But it sounds like sometimes those small tricks does help you also get a lot of gains from your model, given you already fix your data using the best frameworks you can. So can you share some specific tricks you learned from Kaggle? Like what are for example, what are some specific tricks for if you can use to make your model perform better?
Yeah. So one that I love because it's like a really funny idea is called Test-Time Augmentation. So I think almost everyone knows about like data augmentation, where you flip your images, you take random crops and all that stuff. So at Test-Time Augmentation, when you actually do inference, you augment your image and basically take a bunch of different images. And this is where we get into the section of, we basically have an ensemble of images and we take a prediction on that, and then simply take the average of that prediction for our final one. And that kind of works in a way, especially on images, because you have these random augmentations of your test image. And by using these augmentations, you basically get a more stable prediction on what it actually is, and not just because it was rotated in a weird way, now your dog looks like a muffin. But if you take all the specific crops and like rotations and maybe some color shifts, you can actually see that this is in fact a dog. And then 9 out of 10 of your images that you generated out of your original image are actually saying, this is a dog, and one says, this is a muffin. So you say, this is a dog, and you're right because your augmentations worked on it. So that was fascinating. I really liked that one.
Mm-hmm.
Then there was another one that was kind of fascinating. So there is this neural network architecture, which is called a U-net because it's shaped like a U. Like you start big, then you go small, and then you go big again. And there on the end, you can tag something on that is called hypercolumns, which is essentially you take all of those and go back again to all the intermediate layers and have predict on all of those again. So a lot of those Kaggle tricks are using information that you already have or that you can cheaply generate and stabilizing your prediction, your final prediction by having multiple predictors, having some kind of ensemble. Yeah. And other things that I kind of got from it is that neural networks really like shortcuts. So ResNets essentially work because they have a shortcut over these ResNet blocks. UNets work because they have a shortcut. So unless you're cheating with your data, shortcuts can be really valuable if you make custom architectures. So you should definitely consider them. Tricks like that. And yeah.
What about scaling your model from one GPU to like multiple machines?
Turns out it's really easy. So Keras has done most of the work for you. And I find it kind of funny when you talk to like serious researchers, they all want to work in JAX, but they work in PyTorch and they hate TensorFlow. But in my experience, Keras is enough for most of things. And I think we're seeing that development as well with PyTorch Lightning right now, because you have to write a lot of boilerplate code for PyTorch. So getting PyTorch models onto like a distributed architecture can be a bit difficult. You have to adjust all your devices and all that stuff. And in Keras, you literally just say, use this strategy for my model, and it works. And I think PyTorch Lightning does it very, very similarly. So yeah, like I was surprised that people really thought of this, and it was so easy to do. And also with a TPU one where you have to basically put it on a different architecture, you in TensorFlow you just use scopes, and you can really see that TensorFlow is in a way made for people that work on industrial scale distributed systems that have like oftentimes different GPUs and all that stuff. And I think PyTorch definitely at this point has caught up. Like I think they're basically the same library, just a little bit different flavoring. And I'm gonna get terrible words from both sides for that one, which is okay. I'll take it. But in the end, like, yeah, like distributed training is easier than you think, unless you have actual like distributed data centers where you not only train on like one cluster, but you have multiple clusters. Then it gets really hard, and I'm very happy that I don't have to do that.
Yeah. No, I think it's okay to have opinions on, architecture. So in your day-to-day work, do you have a preference of Keras or like PyTorch?
No.
So do you...
The funny, I think it's very funny. I did most of my PhD with Keras because if I needed to do something fancy, I would just write a Lambda layer or do some connections differently. But everything that I needed to do was basically possible in Keras. And then in my first job, they really liked PyTorch. So at my first industry job, I used PyTorch, and which is, I think, the other way around as people see it, because usually people are like, if you do research, you have to do PyTorch, and you see all these graphs that all the papers that are submitted to NeurIPS are either JAX or PyTorch at this point. And it's like, yeah, that's fair. But like most companies will use TensorFlow anyways. And I literally don't care. I think if you understand the systems behind the models that you implement, if you understand why you're doing these things, it doesn't matter if you write the one flavor or the other. Like, because also, each library has some drawbacks. In Keras and TensorFlow, it's very easy to build a neural network that can work on arbitrary images. So you can train it on any size of image, and then you can give it any other by just saying the input dimension is none, 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 which is awesome. That makes life so much easier. And it takes a lot more work doing that in PyTorch. Yeah. I know that Torch Vision mostly has now arbitrary image sizes as well. But if you want to do it by hand, it's very hard, like in my experience. Yeah. Maybe I just didn't find the right way. But on the other side, obviously people love PyTorch because it used to have the dynamic graph rather than TensorFlow 1 with a static graph, which now has changed, which is why I think they're mainly the same at this point. Yeah. But you can also see some things are implemented a little bit different. There's the ensemble that a lot of people use for like matrix multiplications. And it works a little bit differently in PyTorch than TensorFlow. So you have to be a bit careful sometimes translating one to the other. But in the end, like just build a good model. Like I just wanna build something useful. I really don't care which language it is in. And I really like to speak both languages as well, because it's like you can then just play around with anything. And if you find a really cool paper, it is going to be implemented in one of the two languages. And if you say, oh, but I'm only working in PyTorch, and you disregard the TensorFlow paper, but it's a fantastic paper, then you're losing out. So yeah, I'm like, I really don't care.
Yeah, I think it's important to focus on the problem instead of, picking a side on the tools. I think we all have our own preference, but it's important not to completely, discard the other one. As a scientist or engineer, we don't have to pick sides on that. Yeah. And you previously talked about how to create reproducible science. Can you share some tips about that?
Yes, I can at least try. So I'm actually preparing a talk proposal for it right now. But some of the things that I see is that, so during my research, I thought a lot about validation. And now when I or my colleagues review papers, we can see that especially early PhDs often write these really cool papers and have like a proof of concept, which is fine for science, right? You only have to show that it works once. But if you don't set up your validation correctly, you haven't actually shown that it works. And that's like a huge problem. If you already wrote and submitted your paper, you've done so much work, and you already went through your supervisor and all your stakeholders, and then you finally submit, and then there's me or some other person that isn't so nice, maybe even reviewer too, and they say, yeah, no, this is rejected because this is actually not a scientific result. So that's the worst case. But you can also see that if you write your code fairly clean, like I know we're scientists, we care first and foremost about science, not so much about code. But if you write it a little bit clean, like have nice names for your variables, which isn't A, B, C, D, but it's actually this variable is called table because I have a table in this. This variable is called precipitation because I have my precipitation in there. Then people will read your code, understand it, and they can use it. And the nice part with that is if people use your code, they have to cite you. So you get more citations. And then of course, the sharing your model, the model weights at least, is really good because then people can build upon that. So you can take a model from someone else and use it on your problem, fine-tune it. And again, if people do that, they have to cite you. It's good for you. So definitely do it. But then you can go even one step further. And we all know how terrible it is to get PyTorch, TensorFlow, whatever, working the first time. Yeah. You have to install just the right cuDNN and just the right CUDA drivers, and then something still doesn't work. And then you want to try out this really cool new thing, and you have to upgrade everything. So if you can actually provide a Docker image, so a container that has everything installed and just a run command, that is, for me, that is like very close to golden standard, where you can say, this is exactly how I trained it in this environment, and you just have to hit run to try it. And of course, this depends on open data, which in a lot of industries you don't have. But at least you can verify that the code is running, how it's working, and how someone got it to work. I've had it so many times that I got this. So one of the most important papers, but least cited papers of my PhD was this thing that I found from MIT, where I had to like define some environmental variables to point to something so that the neural network could go here and there. So it's, having that in a Docker container is so much more valuable, because then everyone can go there and reuse it, and it can actually get implemented and further both science and humanity. And this is, of course, the positive, what does the researcher get out of it in a way. This is also the altruistic, well, humanity benefits from this way, but it's also, we're doing science, and one of the tenets of science is that it's reproducible. So reproducibility in itself should be a goal. I know that often it isn't, especially in publications. You usually publish once and then you're like, it's done. And like
I
replication
0.111% compared to SOTA. So I'm done.
And I think like you benefit really a lot from it. And also I heard about this story where they had this old neural network in a thing, like in a system that is still from the 80s in an industry application. So in a company. And they basically had to throw it away because they couldn't use it anymore. The code was very, very complicated. The data wasn't really there, and like they could keep it alive, but it is a risk, because if you work in industry, what's it called? Technical debt. Technical debt is a huge problem, and with neural networks or machine learning systems, you can incur that debt much, much easier, because these are state machines that are somewhere and they can work until they don't, and then you usually have a catastrophic failure, in the sense that they will still work, but they might just predict the completely wrong thing. So making sure that everything is reproducible. And I mean, in the case of like, if you look at Amazon, Google and stuff, they always retrain their models. So it's so reproducible that they can just click a button and it automatically gets retrained, right? That is like the industry standard in these big companies then.
I know there's a website called Papers with Code for people to try to reproduce the model. I think it would be nice to have like papers with code with containers. So we can solve that environment problem. I think that's oftentimes we probably spend more time than, writing the code.
100%. I agree so much. And I love Papers with Code. It's like one of the best websites that ever came out, in my opinion. Like Archive, Papers of Code, and they work together as well. So this is really cool.
So you were doing your PhD, and now in your current job, you're also doing a lot of research. So compared to the industry and academia, what is the difference? What are something specifically in your current work you only learned by doing research in industry?
It's kind of funny, because when I was a student, everyone always... most people really like to talk about there's industry and there's research, and there's no in between, right? And now at my current job, I kind of don't agree anymore, because we're definitely, it's difficult what we are. We're an international organization, so it's a little bit outside of companies, but we're still a company. We have to pay for a computer. Like we have a very big computer that needs to be paid for, and energy is very expensive at this point. So we somehow have to get funding for this, and we're not a university, so we're not a research institution. We have a product that comes out of it, but So I'm right now at the intersection where I have a fairly good income, which is very nice. Like, I'm only saying fairly, not fairly decent because I'm trying to be humble, but like, I can't believe what I'm being paid for doing the job that I'm doing. It's fantastic. And I think a lot of people that do machine learning and data science feel the same way. But essentially, I do get to do a lot of research and build to a common goal. And I feel like this is like the huge difference that you have in academia versus industry. I feel academia is very isolated in a lot of ways. And especially with mental health, you can see that a lot of PhDs are struggling because even though you have like a group and you have a supervisor, in the end, you're fighting for your own and you're trying to really get your own thing working. And it kind of never changes because then you become a postdoc, then you become a professor, and you're always kind of working on your own thing. And now in industry, when I was working in industry directly, it was very much we're working in a team. We have stand-ups in the morning. Everyone talks about like, what are we working on today? Which common goal are we focusing on? And it's very much like this group project where everyone is actually contributing, which is fantastic. And now I have a bit of a mix. So I still get to work on a lot of the research part alone, but I'm working towards a bigger goal, this huge system that is supposed to predict weather as accurately as possible for the entire European countries. So, yeah.
Yeah. And I also know that you shared with me last time we chatted that you didn't pass your first PhD defense, and then it was very stressful. Could you share with us about the experience and how did you manage your stress?
Oh yeah, definitely. That was traumatic, to be quite like it was in February 2020 at that, which like at the time I thought, well, this is the worst thing that's going to happen this year. And it wasn't, but it was still very, very bad.
Yeah.
And yeah, what happened was that my supervisor and all my co-supervisors were quite happy with my work, as happy as you can be with a PhD. There's always more work that you can do. But because, like I mentioned, I probably have ADHD, I did a little bit of work in a lot of different places. So there wasn't a good story to my PhD thesis. And my examiners didn't like that. They were, as far as I know, I can't really speak for them, of course. As far as I know, they were okay with the science and like the formality was okay, but they didn't like how it was built. And so they rejected it a week before my defense, which was like, that was terrible. And I don't know, like, I don't know if you have to put a trigger warning for this, but like when my supervisor called me, he was in tears and he had me promise him to not take my own life. And that wasn't because I was saying anything, but he knew how devastating something like that can be on a PhD student, because you're spending 3 to 7 years on this thing and your entire identity is wrapped up in this thing. And like I wouldn't have been the first one that had something terrible happen afterwards. And interestingly, I was really okay at that point because I have ADHD. I get too interested in too many things. So my PhD wasn't the only job that I had. I was teaching at that point. I had my blog. I had YouTube. I had so many identities that my identity was like a mosaic where now a piece was missing. And like, it sucked so much. It was terrible. And I'm still recovering from that as well. Like I'm not over it, because afterwards I had to sit down on this huge failure in my life and do the entire thing again and write it in a way that I thought the examiners would accept that time. And they kind of did. They still didn't like it. But I had to remove like, I think around 6 publications. I wrote a lot of publications in my PhD. I still have no idea how I did that. But somehow I had over 10 publications at the end. And I couldn't put all of them in because I couldn't make a congruent story about machine learning in geophysics. So put most of them in the appendix because like they still have to count because you have to say, I did all this scientific work, give me a PhD. But yeah, I had to rewrite the entire thing in isolation in Scotland during a pandemic. And that was rough. So really mental health in a PhD is really important, I think. And I recommend to everyone to, first of all, get a therapist, like talk to someone, because it gets very lonely. It will definitely, like whatever you do, because so much is hinged on you doing this thing.
Yeah.
And also get hobbies. Like I love weightlifting, I love climbing. And like if I'm having a particularly bad day, I can still go to the gym and try to hit like a very, very difficult lift or something like that, very high weights. And that takes my mind off it. And that's far, far better for you, for your health, than doing something bad, right? And in my opinion, and it's also what a lot of data shows, as far as I know, most PhDs will struggle with depression at some point, or anxiety, or both. So having a varied identity in a couple of different things that can catch you when one of them fails is super valuable, and I would recommend it for everyone. And so in a way, I don't want to be in academia anymore. And like I would rather be, I was like almost homeless very shortly, but without a job for a little bit longer. Right after that, right at the beginning of the pandemic, after my PhD got rejected. Yeah. And that was an experience, but like what doesn't kill you makes you stronger, I guess. Yeah. So at this point, I can literally say about anything that happens, I've been through the worst. Like I got my PhD rejected at the beginning of the pandemic, and that for a reason I still don't quite understand. So it's kind of like when people judge me these days, it's like, what are you going to do? Like you can't reject me, like my life work essentially, and my future career. So that makes life a little bit easier now in hindsight. But in the end,
that's a great perspective.
Yeah, it really helps. And I think I've worked through a lot of that with friends, with just talking to people, with journaling as well. So all those cliche things that people tell you to get better, it sucks, but they work. Yeah. Yeah. You don't want to hear it, and never tell anyone to try yoga when they're depressed, but yoga really works if you want to do it from yourself. So yeah, that's also one of the differences to our industry in a sense, right? Because like the worst thing that can happen now is that someone fires me. Yeah. And then you just get a new job because you're a data scientist and we're kind of in demand at the moment.
Right. Yeah. Yeah. And thanks for sharing your journey. I can relate to that. I didn't do my PhD, but in my master degree, we need to do a kind of qualification exam, and I also failed not just once, I failed twice. Because in addition to the theory, you have to write like a short thesis. I think at that time I was also struggling with speaking English. I moved to the US from China. I think I only lived in the US for 2 years. Only passed the third time, and that's kind of an exception. So I can sort of relate it to how you feel. It's like I spend a lot of money and time, and if I fail, like how am I going to tell my parents, my friend? There's a lot of also not just the frustration, but there's also shame around that. And then sometimes just also because you feel a lot of shame, it's hard to actually study because you're thinking about the consequences. I don't know. I actually don't know. I didn't do a lot of things you did. I don't know how I came out of that. I think it just have to like push myself. And I think if I know what I know right now, I would do it differently. Maybe talk to friends, talk to my advisor more. I think just because I feel so embarrassed, I didn't talk to my advisor that much at that time. I just kind kind of worried that he will get disappointed, I think definitely look for support. I think it's great that your advisor are very empathetic and, try to help you. So for the audience, I think at work, sometimes people might experience the same thing, right? Like if you put on those type of, get a bad performance, have that stress, I think work with your manager, talk to your friends and talk to your family. Besides yourself, other people are not really going to make you feel shameful. It's just all in our head. And then it's important to know there are a lot of things that bigger than a job or degree. It's easy to say, but sometimes it just, it can get very stressful. And I also know that you worked in the US, Europe, in different locations. What are some differences in those type of work cultures?
It's interesting. First of all, also thank you for sharing that. I think it's interesting because shame thrives in isolation as well. It always tells you you're alone in this and no one will look at you. And especially underrepresented minorities will suffer from imposter syndrome always. And that's a huge thing that kind of is the undertone under all of this as well. Mm-hmm. But work cultures, it's interesting. I think in Europe, we generally have a lot of legislation that I remember I watched too much TikTok, and one of the TikToks I saw was about this guy that came to the London office, and London is still known as a workaholic culture. Don't get me wrong. In Europe, they work way too long, and McKinsey is there and all the banks are there. But this guy came there from the US to start the new office and basically was talking about, and you're really lucky because this is actually my last week. I'm quitting and then I'm working as a consultant, so I can take a couple of weeks off for traveling, and I can take care of my kids more and just work 40 hours a week. And I suggested to my manager once that I could take a meeting during vacation, and he looked at me, no, you won't. They would get into legal trouble if I did that.
Oh, wow.
If I don't take enough vacation, my company can actually get into legal trouble and they can get investigated for that. Wow. It is maybe not my current company because it's very, very funny with the legislation, but normal companies, if you don't take your holidays, if you don't take work breaks as well. So it's different per country, right? Every country has their different laws. But in Germany, if you have an 8-hour workday, you have to take a half-hour break in the middle. You can't take it afterwards. Oh. Mm-hmm. You have to take a half-hour break. Yeah. And things like that. I have pretty good vacation days. It's 30 days per year. But legally, I have to have 25. So it's 5 weeks off per year. Mm-hmm. And it's not this weird, unlimited vacation time. But it's actually I tell my boss, hey, I'm not going to be here from then to then. And they're like, okay. If it's not in a job where you have customer contact, then why do you have to plan when people are there? It's literally your work will get done eventually. Mm-hmm. Yeah. And it's in the US, there's a lot of workaholic culture. I feel I have a lot of meetings with US people, and it seems like y'all are working from 6 in the morning until 8 in the night. If it's an early evening, sometimes 10, and that's just so rough. And of course, there's a couple of other things. We have healthcare over here, which means you're not bound to your employer for healthcare. It's just from the state, and I don't know, literally, if I want to go to the dentist, I could call them and say, hey, I need an appointment, and I get one tomorrow. So it's a lot more chill over here. And I feel like we still get a lot done because everyone's well rested and you have your brain capacity, and you're not sleep deprived. And I especially don't want to rag too much on anyone in particular, because like in the US you have, especially in tech in San Francisco, you have fantastic salaries. Like I know that some people at Google get like $250,000, $500,000. That's a nice salary.
Yeah.
And you almost cannot make this outside of a financial sector in Europe, I think. Some people will correct me, I'm sure, but it's very difficult to get those kind of fantasy salaries. But we also don't have to pay for a lot of things. Like we don't have healthcare costs, so it really levels out. And it really helps to see that your colleagues are taken care of in a way. And it's a very like, I feel like even in a capitalistic company, people often take care of each other a little bit, and I like that. Like I enjoy it a lot. So for me, it has been the right move to kind of stay over here, and also seeing what happened during the last president during the pandemic when they canceled the 603B visa or something like that for a lot of people. Like I was very happy that I did not take some of the jobs that I was offered, like in San Francisco, in Los Angeles, in Seattle, because Austin, Houston, because that could have been very dangerous. Because what happens if you suddenly don't have your $500,000 income anymore? Like you are used to a certain level of
lifestyle,
cash at this point, and it flows out very fast. And so having like, if I lose my job here, I have like, I think you call it social security as well, and it's like I can survive. Like I'm getting a year of like a reduced salary after that, up to a year to find a new job. And it's like it's fairly nice to have like a social democratic system, I think. And I think it takes a lot of my financial insecurities and financial anxieties, and that is worth so much like life quality for me. I'm sorry, that was very, I love Europe, but I kind of do. There are really like, there are some annoying things over here as well. But
thanks for sharing that perspective. I think also during the pandemic, I think the companies in US also start to, make sure, have people have boundaries between work and life. And I think there may be some extreme cases, but if you're listening, I think maybe some people, if we take a 6 a.m. or 7 a.m. call, usually manager will be like, oh, if you want to leave early, that's fine. I think there's a more flexible, but I think definitely compared to Europe, you have more law to enforce those type of days off or rest, and you have less pressure if you lose your job. So thanks for sharing your perspective. And then sometimes if you live in Silicon Valley, you just feel like everybody work and think in the same way. So it's great to get different perspective. And during our conversation, you mentioned a lot of tip and trips and papers. So how do you continue to learn in your machine learning journey?
For me, it has really, really helped to start my newsletter. And like, this is not a pitch or anything. It's genuinely the most fun I had in content creation in a long time, because it's this small thing with a few people that actually are interested. Like they sign up to this thing that I make, and they open it, they read it, they click on the links that I share. And it means that each week I have to show up. I have to find cool things that I love. And like, even if it's a slow week, like so I share these 3 curated links, and it's like, I have to find 3 things that I liked. And it really pushes you out, but it's not straining. So it's not hard in a way. So for me, this type of content creation and also writing about these interview questions, like writing the answers for them, that really helps me to dive deeper into these types of topics, like the example with the missing values, like really understanding something in depth to be able to explain. And generally, I've realized that for me at this point, I have a good breadth of a lot of knowledge. So I've now started more teaching, which is like YouTube, and also in-person teaching, which helps me to really focus to understand something so good that I can explain it to someone so they understand it. And like I subscribe to a lot of newsletters. I read blogs. I have Twitter lists with a lot of like people that share really interesting stuff. I mean, I don't know if you noticed, but I stalk your LinkedIn fairly regularly and just see what your interviews are saying. I forgot his name. I think it was Nick from Airbnb. I love the interview with him as well. So podcast, very important. So I'm not only honored to be here, but I'm also very happy because I'm like, those are really interesting interviews. I'm very happy to be here.
Yeah,
but so this immersion aspect right now is very important for me. Just listening to podcasts on the way to work. I have like a half-hour commute, and just data science, machine learning podcasts are fantastic for just hearing how other people think about this, and then in that way learning about it. Like when you and Nick were talking about this novelty effect, for example, I was like, oh yeah, I heard about that before, and this is really important if you do social sciences. And now it's like at the forefront of my head when I read new things, and I'm like, oh, is this actually a thing, or is this just novel enough? So yeah, like that is just a way for me to stay updated in these, like learning from peers, essentially.
Yeah, thanks for sharing that. I'm glad it's useful. Can you share some other newsletters you follow that you recommend other people to check it out?
Yes, absolutely. So for data visualizations, there's Charter, which is chart with an R at the end. And they make some really nice visualizations themselves, where they dive into like different, like recent topics often, but also just interesting topics. And they're built in a very interesting way. And I think a great way to learn like how to do like data communication in a way. And I think every data scientist at some point has to communicate their results. So getting some inspiration there. I really like the TLDR one, which is more general tech, but it always has some interesting GitHub repos that I can find there. I do actually read Morning Brew as well. Like I know it's terrible and they sponsor like everyone, but the emerging tech one, I read those and I'm like, this is really in depth. Like they explain what transformers are in some of their stuff, and I'm like, that is like some in-depth knowledge, and it's actually impressive in my opinion. Like the reporters that are doing that work, like genuinely good. Like I was surprised. I didn't think it would be that good because it has like so broad appeal. But like genuinely, when they write about a topic and have a writer on that, it's actually, like in my opinion, a lot of good journalism. Those are fairly big ones.
Yeah. And do you have any books you like about machine learning or data science?
A ton, yes. To be honest, so right now I'm actually writing Twitter threads with books that I like. So it's probably easiest to go on my Twitter or go on my Amazon shop where I list them all. But it's so for machine learning, like and data science, there's the book from Aurélien Géron, which is, he's also one of the core contributors to scikit-learn. I think it's hands-on machine learning with scikit-learn, something like that. It has a little salamander on it, and I think that's a fantastic book. There are so many good books, actually. So there's, if you want to learn about like natural language processing, there's the one from, I only know his Twitter handle. We just connected on LinkedIn, and I'm really sorry that I forgot the name. It's Luton, and it's a natural language processing book with Hugging Face, essentially. And that one is like a fantastic one as well. Matt Harrison has a really nice book about effective pandas. So if you do a lot of like data engineering, a lot of pre-processing, and you use a lot of pandas or pandas-like libraries, I think that one can teach you something, even if you're a pro at pandas. Like, there are fantastic books, I think, like, genuinely. I don't want to plug my stuff too much, but like I'm genuinely, I'm writing up a lot of them right now. Yeah. I did a ton of research into which ones are good, read a lot of them, and I'm sharing them cool. Right now.
Yeah,
so thank you for that,
your
Volley.
Twitter handle to the notes so people can check it out. Can you share some mistakes you made in your career?
I find that one always really hard because you always learn in a way. But I think, like, I don't want to be ungrateful for my PhD examiners, but I think it would have been good in a way to be more careful with the selection of that committee. So if you have people evaluating you, make sure that those people don't work in something that is kind of detrimental to what you do. So one very, very silly example is if you're working with frequentist statistics, think twice about getting someone that works in Bayesian statistics, because they might ask some very, very hard questions. So selecting people is quite valuable. And when I at the old company, when I was involved in the hiring process, I think I was able to glean a lot of insight in that, because you only want to hire a position once. So really be careful who you hire. And if you don't find a suitable candidate, go for a second round rather than taking someone that you're not going to jive with, that is not going to fit the team. So that was definitely, like, that was not the greatest decision in that case, I think.
Yeah. Thanks for sharing that. So what do you think about the future of machine learning?
I think it's very interesting, because when I talk to people that aren't in machine learning, I hear a lot of times, but machine learning doesn't work. And it's so weird, because I work in this and I see it working everywhere. Like, if you use Google Lens, you can translate text. Like, I was in Taiwan and I was translating Chinese like on the fly, and it was fascinating. And like my colleagues that are coming to Germany right now and are having trouble with the translation, just translate it right away. Google search is using BERT. Our predictions for the weather are soon using machine learning. So I feel like it works. So if people are worried about like an AI winter, I don't see that coming, because I feel like all the failures that people like to write about, like this famous, like Gartner wrote about this data science failure where a data scientist came into this company and then he was working on this thing and then he showed it to the company, and then the domain scientists were saying, oh, but we already have a solution for this. And I'm like, that's not a data scientist failure. That's a management failure. Why was this? Yes. Like, why didn't he communicate with the stakeholders? Why didn't he communicate with the people that he's building this for? So this, like, I know that I'm kind of like relabeling this in a sense, but I feel like most data science failures are either like culture failures. So a company that doesn't have any data can't do data science, and communication failures. So if you don't talk to your stakeholders, if you don't talk to like the domain scientists, the domain experts, then you're going to have a really hard time, and you're probably building something that no one actually wants. So those are definitely like failures that happen. But I feel like overall, I see so many successes, which also means that more people are coming to the field. And I think we see that, right? Like in our comment sections, you're a much bigger creator than me. You have like so many followers and so many people, and I'm very small and much more niche, but I see that so many more people are interested in this every day, and you see new people all the time with like bright eyes and like really cool ideas and building these amazing things and new fields like weather, geoscience, like building these entirely new apps like based on GPT-3 as well. Even if they're not doing machine learning, they can now use it with APIs because other people make it available. But that also means that there is going to be a little bit of a shift, I think, because a lot of the things that are fairly easy are going to get automated. And I think you see that with like no-code platforms and a lot of the AutoML platforms. So there is going to be space for people that are very good at combining things. So like myself, I do real-world machine learning. I do machine learning with physical data. That is two skills that are very hard, and me combining them, I'm going to have a good career with that probably. Like, it's going to be quite hard to replace me because it takes like a 5-year degree to learn physics and then a PhD on top of that to learn machine learning. You don't have to have a PhD to do machine learning, but it took it for me. And so it's going to be like these specialists that work on these really hard problems. And then there's going to be a little bit of a divide. And I'm kind of scared that people are going to be struggling to find a job in between, because there's going to, like, we're very good at automating our own jobs, unfortunately. So there is going to be a little bit of this chasm in a way. But if you can combine something you already know with data science, that is going to be quite valuable. And also, sorry, like I'm gonna add another one. I think you also shouldn't underestimate smaller businesses. Of course, like Google, Amazon, they're fascinating companies, and working there makes your CV like golden, basically. But if you work in small companies, you still get a really good salary. And oftentimes you can already get a lot of value from getting their system out of Excel into something more robust. Getting some automation set up, getting their payment system set up. So even if you do data science not on a global scale, on building the biggest, baddest model in machine learning, then you can still bring data science or data-based methods to smaller companies that are having so much value from this, because you're suddenly bringing them into the digital age in a sense, and you can build such a fantastic career just on that alone, because there are so many of these companies. You can basically find one by just going outside into the next shop and see what happens. Of course, you have to somehow find a company that wants this, but I think more and more they have to do this for staying competitive. So that there's definitely like a market opening up in that direction for the people that would get automated away in the classical, more data analyst and more automatable jobs that are there right now.
Yeah. I think data analysts in the future can use some low-code tools to train ML model, but I think we'll still need researchers to develop those models or like improve performance, especially like you mentioned, you're dealing with a lot of sporadic data or other challenges. So data science is not going away and it's not a fad, but I do agree with you, kind of similar as what I talked to another guest. We talk about neuroscience and AI. If you are in this type of intersection, like you are in physics, you are doing something really, really unique, and it's really hard to be replaced. So be good at what you do with data science, and also be good at industry, learn the domain knowledge. And then I think that's going to make this data scientist really valuable.
Absolutely. And I think this goes into this concept of like T-shaped knowledge. Like you have a breadth of a lot of things, and then you're an expert in something. And I guess what we're talking about, like I know this is getting like super like business speaky, and I feel a little bit weird about it anyways. But then you're like a pie-shaped individual because you have machine learning or data science here, and you have your expertise here, and then a breadth that spans across it. So
yeah,
be more pie.
I like that. It's the first time I heard of this pie-shaped individual. And I think, people call us a business or whatever, soft skill fluff, but I think it's actually very important to help us to, think about our career. And a lot of times, all the hard skills you learn are important, but it's the decisions you make in your life that really put you on a different type of stages of your
100%,
career.
yes.
So thanks for sharing that. And before we wrap up, what are something currently you are working on, you're excited about in your career or in your life?
So one of the things that I'm still wrapping my head around is how to make machine learning work on a sphere, because we're building global models. So a picture is nice in 2D, so you can do convolutions. But what happens if this side is suddenly the same as this side because it goes around? And this geometric deep learning is so fascinating because you can do so many different approaches. You can work with graph neural networks. You can work with like periodic convolutions that somehow understand that you're wrapping around at the backside of the globe, essentially, and things like that. And like reading about this is so cool because people have found these very interesting ways to approach it. So I'm going very, very deep in that direction right now. And I think generally like graph neural networks are just fascinating. I worked with some point cloud data before, like the stuff that is basically used by Teslas to drive, I think. Like the older models, the newest don't really have LiDAR anymore. But like graph neural networks, I think they have a lot of potential, but they are really hard because, like the math isn't as intuitive as maybe a convolution is. So but I've been reading up on those because it's quite valuable in understanding like non-Euclidean machine learning.
Yeah. And before we wrap up, so if folks want to read more about your journey and books or learning you recommend, where can they find you online?
So my main source of truth is my website, which I'm sure you'll link somewhere because it's my last name, and my last name is very hard to pronounce and to spell. It's very German. I have 7 letters in there, and 1 is a vowel. But essentially, so on my website, I have a small blog, so I always write about what I'm thinking at the moment, and I share a lot. And if you want to catch up on a like personal level, Twitter definitely. Like I still like Twitter, even though it's changing. Possibly, we'll see. And definitely my newsletter as well. I always have a personal segment in there, like what I'm up to, what I'm thinking about, and that's also a fantastic way to get caught up because I love that small space. It's a very, very like it has a very warm place in my heart.
Yeah. Thanks for sharing that. I will link it in the show notes. Thank you so much, Jesper, for coming to the show. I really enjoyed talking about machine learning, weather forecasting, and Kaggle tip and tricks and your career journey. Thank you.
Thank you so much for having me. This was a lot of fun and really insightful as well for sharing your journey. And thank you so much.